Welcome to lesson 5.6. Talking about complex numbers. So what does that mean? What is the point of that? Well, suppose you got an equation like this. I don't know, x squared plus 16 equals 0, something like that. There is no linear term, right? So you would subtract the 16 over based on how we've learned how to solve up to this point. And you get x squared is equal to negative 16, right? Because we subtracted 16 from both sides. Now I take square root of both sides, and x is equal to plus or minus square root of negative 16. So the question is, what is the square root of negative 16? Some people would say, oh, it's negative 4. The square root of negative 16 is negative 4, but remember, negative 4 times negative 4 is equal to positive 16. So it's not the square root of negative 16. Then sometimes people would say, all right, it's negative 4 and 4. Well, that's not a square root then if it's two different numbers. So the point is there is no real number that is the square root of a negative. So we developed imaginary numbers, and that is what this entire lesson is going to be about. So it's going to be background for what imaginary numbers are. Complex numbers is just an umbrella term. So you don't need to write all this down, but if you were curious, complex numbers is the umbrella to which real and imaginary numbers split out. And then within real numbers, then you've got rational, you've got irrational. And then underneath rational, you would have subsets of rational numbers are integers. So hopefully these are all terms that you are familiar with. Whole numbers or natural numbers. All right, so pretty much all the math that you've done has been some of those, right? Up to this point. So now we're going to branch out and talk about imaginary numbers. Complex numbers are both, right? So complex is the umbrella term for both. So the objective for this lesson, we're going to identify and graph complex numbers. We're going to add, subtract, and multiply complex numbers. So there's a lot of background information on complex numbers before we start using them to solve quadratic functions. So it'll seem like this lesson is a deviation from what we've been working on, but it's going to be the background information that's going to get us to where we're going to go. So definition of an imaginary number, any number of the form a plus bi. So where bi is the imaginary number. So now the question is, what does that I stand for? So this is the definition of I. I is a number whose square is -1. So that means another way to think about that is I is the square root of -1. Okay. Then for any positive real number a, the square root of -a is equal to I square root a. So essentially what happens here is you split up -a into -1 and a, right? This becomes the I. The a stays. So what we're going to do in example 1 is just simplify some radicals that have some negatives, or that are all negative, that are all negative. Square root of -25. Well, you know what the square root of 25 is, right? Think about it as separate. Square root of 25 is 5. Square root of -1 is I. Okay. For 81, 81 is another perfect square. So I'm just going to split this up into -1 and 81. Square root of 81 is 9. Square root of -1 is I. For C, 12 is not a perfect square, but it has a square factor, right? So that pair would be 4 and 3. And then since it's negative, I'm going to split it up as -1. So just think of like the negative as another step. Square root of 4 is 2. The 3 is going to stay. The -1 becomes I. So since the 3 stayed, it would be that. 2I root 3. All right. Square root of -98. 98 is not a square, but it has a square factor, which is 49. So the 49 comes out as 7. The -1 comes out as I. The 2 stays. And hopefully you get it, but square root of -16, right? 16 squared is 4. The negative makes it I. Okay. So complex numbers are a set of imaginary numbers and real numbers. So as I was saying with that flow chart, essentially, well, it wasn't a flow chart, like an organization chart where I had complex numbers split into imaginary and real. A complex number has both. The A is the real part. The BI is the imaginary part. Complex numbers are considered in standard form or simplified when they're in that order. So the real number comes first, the imaginary number comes second. Here, square root of -121 is 11I. How would I put this in simplified form? The -7 needs to come first. So the real number comes first. Since that's positive, it would be plus 11I. Same thing here. Square root of -9 is 3I. The 4 comes first. So you got 4 plus 3I. Part of the objective was graphing. So you've got a complex number plane. Locate the real part of the number on the horizontal axis and the imaginary part on the vertical axis. The labels on the vertical include the I. So essentially, if you have a complex number, you think of the real part as the X, the imaginary part is the Y, and you would plot it as such. So -3 minus 2I. That means on the real part, you go left 3, 1, 2, 3. For the imaginary part, you go down 2, 1, 2. 5I, you don't go left to right at all because there is no imaginary part. And then, I'm sorry, there is no real part. And then since it's 5I, you go up 1, 2, 3, 4, 5. So you can label them, right? 5I is there. -3 minus 2I is there. 4 plus I would go right 1, 2, 3, 4, and then up I. So up 1, 4 plus I. Next part, absolute value of a complex number. By definition, it's its distance from the origin on the complex number plane. So when you think of absolute value of a real number, it's the distance from 0 on a number line. That distance is easy to figure out, right? Like 4 has an absolute value of 4 because it's 4 away from 0 on a number line. -3 has an absolute value of 3 because it's 3 away from 0 on a number line. With a complex number plane, let's go back for a second. Its distance from 0 is not a horizontal line, it's a diagonal line. So for instance, for 4 plus I, the distance of that diagonal line there is the absolute value of 4 plus I. Same thing for -3 minus 2I. The absolute value of 5I is that straight vertical line. So the absolute value of 5I would be 5, and we'll talk about how that happens with the formula. So it's asking for us to do those anyway. So it's -3 minus 2I. All right, so we got -3 minus 2I. We got 5I. and you've got 4 plus I. So if we're using that formula, the absolute value of a plus bi is equal to square root of a squared plus b squared. That is the distance formula if you've never used it. In this case, the a is -3. It actually doesn't matter that it's negative because it's going to get squared out anyway, but I'm going to write it. And then notice how it's b, not bi, right? It's just the b value. In this case, the b value is -2. Now you just simplify. -3 squared is 9. -2 squared is 4. So square root of 13 will be the distance for that one. 5i, there is no a. B is 5, so it's square root of 5 squared, which is the square root of 25, which is 5, which is what we thought when we looked at the graph. For 4 plus I, it's the square root of 4 squared, plus when it's just I, it's as if the b value is 1, so 1 squared. So you end up with square root of 16 plus 1, which is square root of 17. It's just a formula. Since you're doing this virtually, you would have access to that formula. Just look it up or write it where you can have it when you're doing the practice. Last part of the objective was to do some operations. Adding and subtracting with complex numbers works the way, I think, works the way that you think it should. It's, to sum it up, the process is collecting like terms. In example 5, we're just looking for the additive inverse. So take the opposite of both parts. The opposite of 4 is -4. The opposite of -2i is positive 2i. 6i, the opposite of that is -6i. D plus EI, even though they're variables and not numbers, opposites are opposites. Okay. For example 6, this is what I'm talking about. We're just really combining like terms. So I know there's parentheses here. You can almost ignore them. The real numbers go together. -2 and 4 add together to get 2. 5i and -6i add together to get -i. That's it. So those two complex numbers, you're just combining the real part and the imaginary part separately. When there is subtraction, I would write another, add a step, write another line where you distribute the negative. So now it's 9 minus I plus 3 minus 8i. 9 and 3 combine to 12. -i, -8i combine to -9i. Distribute the negative here. You get 5i minus 3 plus 2i. -3 is the only real number, so that goes first. 5i plus 2i is 7i. Last one here. Distribute the negative. You get -7 plus I minus 7 plus 6i. Combine. -7 and -7 add to -14. I plus 6i is 7i. Last part of the objective was the multiplication. This essentially works the way you think it should. However, there's one part at the end that I will show you. So we're going to FOIL like normal. -2 times 4 is -8. -2 times -6i is plus 12i. 5i times 4 is plus 12. 5i times 6i is -30i squared. We will combine the two i's to get 32i. But I squared is not I. Remember what we defined. I is the square root of -1, right? So if I square both sides, you can say that I squared is equal to -1. That's the definition of what I is. It's the square root of -1. So that means I squared is -1. So this is really -30 times -1, which is positive 30. So that positive 30, we're now going to add with the -8 because it's just a real number. 30 plus negative 8 is 22. All right, for this one, 12i times 8i is 72i squared. Again, we flip out I squared for -1, you get negative 72. Negative 5i times 10i is negative 50i squared. I squared is -1, so it's like negative 50 times -1, so positive 50. Here I FOIL 2 times 2 is 4. 2 times I is 2i. Negative 2 times, I'm sorry, negative I times 2 is negative 2i. And negative I times negative I is negative I squared. These two will add to 0. I squared is -1, so that's really like minus a -1, so it's 4 plus 1, which is 5. All right, give the exit ticket a try, and we'll go over it together.